Thank you. Good afternoon. I am Mostafa Dawood, and today I'm going to give a presentation for a novel air handling unit system that can be used to deal with high latent loads in hot humid regions by utilizing solid desiccants. Population increasing is a major challenge that the world faces nowadays. In 2019, a United Nations report predicted that population might jump up to 9.7 billion by 2050. According to a research done in 2020, air conditioning systems consume about 60% of the total energy consumption of the building. This share for air conditioning systems is huge, taking into consideration that we depend most on non-renewable sources of energy. In hot humid regions where the outside latent load is high, conventional air handling unit systems are used. Fresh air at ambient conditions is being mixed with the return air from the room in a ratio that keeps the required fresh air required for the space. Then this mixed air is cooled and dehumidified after going through a cooling coil. However, after cooling and dehumidification of the air, air undergoes sensible reheat in order to be adjusted to the supply conditions of the room. Recently, adsorption cooling systems driven by thermal energy were used to replace electrically driven vapor compression cycles. Unlike absorption, which is a bulk phenomena, adsorption is a surface phenomena that depends mainly on van der Waals forces. The high thermal resistance for solid desiccants affect heat transfer mechanism, which affects the ability of the desiccant to adsorb water vapor from airflow. So metal foams were used to overcome the thermal resistance of desiccants by packing desiccant particles colored in yellow into the voids of a metal foam where it helps to enhance heat transfer mechanism, which enhance the mass transfer mechanism for the vapor. Based on the previous discussion, it can be observed that there is a need to investigate the performance and the feasibility of an air handling unit with the desiccant packed metal foam heat exchanger to deal with high latent loads applications. As previously discussed, the traditional system depends mainly on cooling coil for cooling and humidification of the air, and the reheat coil, which uses electrical power in order to adjust air temperature to the supply air conditions required for the room. The proposed system in the shown figure depends mainly on two fixed aluminum packed beds with silica gel particles, where silica gel particles are packed inside the voids of the metal foam of each bed. Each bed is surrounded from top and bottom sides with water channels to provide cooling or heating water in order to aid adsorption or regeneration. The two-bed configuration was used to allow one bed to perform cooling and humidification while the other bed is being regenerated. Outside air at point 1 is being mixed with a portion of the return air from the room at point 2 in a ratio that satisfies the fresh air required for the space to provide mixed air at point 3'. The mixed air at point 3' is directed to the bed which undergoes cooling and humidification by means of control dampers. The bed which undergoes cooling and humidification has cooling water that flows in its channel of 20 degrees Celsius in order to cool and humidify the air passing through the bed to reach air conditions at point 4'. However, air at point 4' requires to be more cooled in order to achieve supply conditions of the room. Then it is mixed with the rest of the return air from the room in order to satisfy the supply conditions, while at the same time, the regeneration bed receives ambient air from outside and heating water of 40 degrees Celsius flow inside the water channels of this bed in order to regenerate the bed and the desiccant to remove vapor from the desiccant with the airflow. A COMSOL numerical model was set to investigate the performance of the two beds in order to know the conditions of air after the bed. It can be noticed that the levels of heating and cooling temperatures for the thermal fluid can be provided by low energy sources rather than the traditional system. In the psychometric chart process, the red lines refer to the traditional system process, while the blue lines refer to the proposed system process. Point 4 dash in the proposed system represents the downstream values of temperature and humidity for the bed, where this point represents the average values of outlet air temperature and humidity from the bed. In order to mix air from point 4 dash with the rest of the return air from point 2, point 4 dash must lie on the same sensible heat ratio of the line to 5. The computational domain used represents a metal foam packed bed of length 120 millimeter and height 30 millimeter, placed inside a duct. An aluminum substrate layer separates the aluminum foam heat exchanger and the cooling or heating water flow in the water channel, where process air enters the bed from left-hand side as a two-dimensional flow, where any changes in temperature or moisture in Z directions are neglected. The governing equations for the model used depend on mass conservation equation for airflow and desiccant, and it consists of a moisture storage term, a moisture change across the control volume term, and the moisture change inside the desiccant term. The second governing equation represents the interfacial equation which controls the moisture transfer between the desiccant material and air, and it consists of moisture increase inside the desiccant and moisture transfer between the desiccant and air, where the third governing equation represents the energy equation of air, and it consists of change in air temperature and a term to show conduction effect, a term to show convection effect, and a heat source term. The fourth governing equation is the energy equation in desiccant material, where the pressure drop across the bed can be calculated by the Ergun equation, which depends most on the length of the bed and the airflow velocity. The model was validated by the experimental results of a previously published work, where the model tested the same ambient conditions and geometric parameters of the experiment at a cycle time of 800 seconds divided equally between adsorption and regeneration. The values of variables at the end of the phase are taken as initial values for the following phase. The comparison between the model and the experimental results shows a good agreement within 10% deviation in outlet air temperature and 14% deviation in outlet air humidity ratio. The following figures show the air temperature distribution through the two beds, where the lower bed is going under regeneration, while the upper bed is under cooling and dehumidification. For a cycle time of 800 seconds, temperature distribution inside the bed reaches steady state after 200 seconds from the start of the phase. The effect of cycle time on the bed downstream values was studied. At constant inlet temperature for the dehumidification bed, at constant inlet temperature colored in cyan, and by increasing cycle time, outlet values for temperature and humidity from the cooling and dehumidification bed decrease. Similarly, for the regeneration bed and at constant inlet temperature values and the humidity values from ambient, colored in orange, by increasing cycle time, By increasing cycle time, regeneration temperature and regeneration outlet humidity increase, with a notice that the very short cycle time of 400 seconds is not enough to achieve regeneration. The case study investigates the feasibility of using the proposed system to serve 635 square meters indoor swimming pool located in Alexandria, Egypt. The pool is a part of a grand hotel served by water-cooled chiller plant. The calculated supply air required for the pool is 8,149 liters per second to satisfy a 28 degrees Celsius dry bulb temperature and 60% humidity ratio, relative humidity. The calculated space sensible heat ratio for the given case is 0.31. This is due to the high latent load resulted from the activity inside the swimming pool. The monthly outside design conditions of the city of Alexandria for 4 months of summer are listed in the following table, and it shows that August month is the highest latent load month. 4 case studies for the city of Alexandria were conducted at a cycle time of 800 seconds. Results of downstream values of dehumidification bed shows that there is a very slight variance in outlet air temperature and outlet air humidity over the 4 months. This is due to the dependence of the dehumidification bed on upstream air at mixing conditions, as shown in the previous figure. While the downstream values for regeneration bed seem to have more clear variance due to the dependence on air at ambient conditions, which vary among the 4 months. This figure shows the energy comparison between the traditional system and the proposed system, where the blue column refers to the cooling coil load in the traditional system, and the red column refers to the reheat load in the traditional system, while the cyan column refers to the adsorption load in the proposed system, and the orange column refers to regeneration load in the proposed system. From the graph, it's obvious that August month represents the peak load months. This is due to the high latent load during this month. Also, the figure shows that the proposed system consumes less energy requires less energy than the traditional one. This is due to the dependence of the proposed system on desiccant material to handle latent load, rather than dependence on condensation and deep cooling to remove the latent load. The following points can summarize the conclusion. Desiccant packed heat exchanger system can be used as an alternative section for cooling coil and reheat coil in the traditional air handling unit system. A cooling water of 20 degree and a heating water of 40 degree with mixing the return air from the space into 2 stages can be enough to achieve outlet air conditions suitable for the desired space conditions. Increasing the cycle time can achieve a lower outlet temperature and humidity for dehumidification with using the same cooling and heating water temperatures. Desiccant packed heat exchanger system consumes higher running cost for the supply fan in the air handling unit. This is due to the high static pressure for the air inside the bed due to the narrow passages left for air in order to proceed to the supply fan. Thank you.
Thank you, Mohammed, for your wonderful presentation.